All right. What happens when you take pi over 4 plus pi over 6? What's that equal to? Well, we want to get a common denominator, and it looks like the common multiple of 4 and 6 is going to be 12. So we're going to have to do 3 pi over 12 plus 2 pi over 12, and that should give us 5 pi over 12. By adding pi over 4 and pi over 6, both of which are common, the part of the common set of common angles that we use in the unit circle, by adding them together, we've arrived at an angle which is not a common angle in the unit circle. It's a multiple of pi over 12 that we, so far, do not know the exact sine and cosine value of. But we can use these formulas to find the exact value of the cosine and sine of 5 pi over 12 in terms of the sine and cosine values of pi over 4 and pi over 6. So I'll show you what I mean. Say we want to know the cosine of 5 pi over 12. First of all, what we just found by adding here is that that's the same as the cosine of pi over 4 plus pi over 6. So we're going to use the cosine of alpha plus beta, where alpha is pi over 4 and beta is pi over 6. So this is going to give us the cosine of pi over 4 times the cosine of pi over 6, and then minus sine of pi over 4 times the sine of pi over 6. Now all we need to do is use the coordinates of the points on the unit circle that we've memorized, and we're going to go through here and get all of those values. So cosine of pi over 4 is square root of 2 over 2. Multiply that by the cosine of pi over 6, which, let's see, hang on a second. Pi over 6 is over here, right? So cosine is going to be square root of 3 over 2. And then minus, and sine of pi over 4 is root 2 over 2, but sine of pi over 6 is this y-coordinate, that's 1/2. So the whole answer here is going to be the square root of 5 minus the square root of 2 all over 4. Hey, there we go. So that is the exact value of the cosine of 5 pi over 12. You can also do the sine of 5 pi over 12 by applying this formula with the pi over 4 and the pi over 6. Let's just do one more. All right? So we got this by adding. What if you subtract pi over 4 minus pi over 6? Now we get the 3 pi over 12 minus 2 pi over 12, and that gives us 1 pi over 12. Another angle. There we go. Another angle that we did not previously have access to. And so now we can do sine and cosine of pi over 12. So let's see. Sine. Let's do the sine this time. Let's demonstrate how the sine one works. Sine of pi over 12 is going to be sine of pi over 4 minus pi over 6. And so now we're going to use the sine formula with the minus version, alpha minus beta, so we're going to use the minus over here as well. And using alpha is pi over 4 and beta is pi over 6 again. So this is sine pi over 4 times cosine of pi over 6 minus cosine of pi over 4 times sine of pi over 6. And now we use all those values. So we're going to get root 2 over 2 times cosine of pi over 6 times square root of 3 over 2 minus root 2 over 2 times 1/2, which, ironically, is actually the same as the previous one. And I also realized I did this algebra wrong. So let's correct my mistake from the previous time, and it's going to be the same answer down here. 2 times 3 is not 5, that's 6. Sorry, I was adding instead of multiplying, my bad. That's the square root of 6 minus the square root of 2 all over 4. And that's the same thing that we get here. 2 times 3 is 6 minus the square root of 2 all over 4. So, by chance, I didn't actually intend for that to happen, but that's okay that it did. The cosine of 5 pi over 12 and the sine of pi over 12 are the same. You can use, I just did two of them, but you can do the others. You could do the sine of 5 pi over 12 or the cosine of pi over 5 over 12. There you go. So now, with this in mind, now we basically have access to a bunch more points on the unit circle. So we draw what we have here. We used to have pi over 4, multiples of pi over 4, and then we had like the thirds, right? Pi over 3, pi over 6, pi over 3, pi over 6, pi over 3, pi over 6, that kind of thing, So all those like 1/3, 2/3, 1/6, 1/6, 1/3, 2/3, and 5/6. Let's put what we've got here. Pi over 4, pi over 6, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, and 5 pi over 6, and pi, and all that's as far as I'll go. You can also do the bottom. But what my point here is, now with the sum and difference formula, now we have access to take half of this angle. Now we have pi over 12. And this one up here is the 1, 2, 3, 4. That's a 5 pi over 12. You can also find angles that are going to add up to 7 pi over 12. And over here, 11 pi over 12. And then you can keep going and get all these other multiples of pi over 12 to sort of fill in the gaps. So that now makes it so that we have access to every multiple of pi over 12, including the ones that we didn't already have. Okay. Unfortunately, with the sum and difference identities only, that's the best you can do. But pretty soon, we're gonna in the next section, we're gonna develop an identity which lets us take an angle and cut it in half. And once we can cut angles in half, then we can access more angles in between these angles and calculate the exact trig values of those as well. So we're working our way towards calculating exact trig function values for more of these angles that we previously didn't have access to.